Okay, well, hello everybody. I'm Scott Grizzard. This is Calculus. I'm from the University of South Florida, and this is Calculus 1, section R01. See, that's 2311. Details, details, details. As you can see, today we're going to be talking about the fundamental theorem of calculus, and we're going to prove it. This is probably the most beautiful proof in mathematics. Well, maybe not. I mean, some of them are really pretty, but it's one of the most beautiful proofs in mathematics. It's definitely the most beautiful proof we do in this class. And it's highly intuitive. And basically, if you don't think this proof is beautiful, then either I didn't do a good job explaining it or something's wrong with you, because this proof is truly beautiful. Now, I made a typed up notes and I put them online on Canvas. Details, notes. I also put it on my let me pull this up. I also put it on my public web server on USF web server, the public one. So, and I put a link to the PDF in Stream Chat on Twitch, just in case you were not in my class. That way that you can access the notes later, so you can see them, because some people aren't in my class and they're watching this, and I don't want to get bogged down in the details. It's important to note that that PDF with all the details is just that, just the details. I don't want to get bogged down in the details. So we can talk about the notes. Of course, are going to be here. I will upload them after, but they're also all the details that for the proof that you may want to see. And I even fixed a few typos this year, so that's an improvement. Are there any questions before we get started? I will go over the quiz. Just give me a second. Okay. And of course, chat for this is on Discord, because there's only emote chat on Twitch if you want to have questions. So there don't seem to be any questions right away. So I will get to just jump right into the quiz. Oh, a couple things. I made an announcement about it, but the final exam is on Saturday. It is at 3. There is a problem set due. I just posted it. Technically, it's supposed to be due on 11:59 on Wednesday, along with and technically the last day I'm supposed to allow you to do makeups is Wednesday at 11:59, because there's not supposed to be anything due on a reading day. Now, I don't think I'm going to get any objection. If someone does object, I technically have to move everything back to Wednesday. But something tells me that you guys will be fine with the idea of it being due on Friday. Also, there is peer leading this weekend. This week. It is optional. You do not have to attend. It will be a test review session with peer leaders. Also, the Wednesday night problem session, because discrete math has an exam as a test on Wednesday, will be moved to 7 p.m. instead of 5 p.m. Thursday, 7 p.m. just as normal. Posted as the bootleg. I have not done the bootleg. I haven't done the place for you to take the bootleg yet. I will get to that. Also posted, the last web assigns are out. One due tonight, one due tomorrow. I may make a third one due on the... I may make another web assign due next week, but it will be extra credit if you want to do it on the stuff I'm going to talk about tomorrow, and the midpoint rule stuff. So, I'm sorry, on Wednesday when I talk about that. But the all the material that's for that is, the rest of the stuff is already up. How many questions are there on the exam? It's a longer exam because you have the entire exam period, but not that much longer. I want to say it's 12 pages. I have to do the answer sheet tonight, and then when I do the answer sheet, you'll see. Are there any other questions? Okay, so let's talk about today's quiz. As you can see, I haven't done the stuff for it. Let's see, the first problem. Let's do the fundamental theorem of calculus. I'm in an extremely lazy mood, so what I'm going to do is take this off the answer key. I'm going to go copy And then I'm just going to go paste because we've said it all again and again and again. How do we feel about the statement of the fundamental theorem of calculus by now? 1 to 5. Stating it, and then what it means. We'll leave this stuff. We need to get rid of this. Okay. No. So the question is, do I have to, again, whatever method, whatever way you want to write it is fine. You may write it like this. You may write it with the orange stuff instead. Let's see, that rubric is here. You may write it like this if you so desire. You may write it however way you want to write it. As long as you've got the details, as long as you've got the stuff, right? What do you need? What do you absolutely have to have? You have to have that G is an antiderivative for F, or that G prime of X equals F. You have to have that F is continuous. Those are two important details. And then you need the derivative of the AUC function. However you want to write the AUC function is up to you. And you need FTC2. The AUC of FA of X equals G of X minus G of A, or big F of X minus big F of A if you do if you use big F here instead of G. Either way, it has to match, but you just have to do it. Okay. Any other questions about that one? Okay. As I said, there's 1,000 ways to state it, and the big one, I think the easiest one is this one, but if you prefer this one, that's fine too. Either way works. Okay, so I need to define the Riemann integral. All right, so let's see. How could I do that? Well, the way I do it when I want to memorize this definition, when I want to repeat this definition, is I draw the picture, because I can never remember all the bloody details without the picture, right? And I just want to write it as a limit of Riemann sum, so I got to say what that is. So for me, what I do is I draw a little picture. So this is how I remember it, okay? So this is right here. I remember that this right here is change in X. And I remember that this is X0, X1, X2, and X3. Okay, so I write them out. And then I remember that this is F of X1, and this is F of X2, and then this is F of X3. Okay, so this is what I do. I draw out my rectangles, I make a little shape, and I do it, I just make a little note on the side. And if I make that little note, then the stuff, the details, all the other stuff just comes from my drawing, okay? So I'm going to say, okay, well, I look at my drawing. Why is there no... I'm sorry, I seem to be having wiring problems on the cooler for my tablet, and it's going to start black screening on me in 2 seconds. Aha. There we go. All right, so what I'm going to do is I'm just going to write it as a limit of Riemann sums. Right? So I look at my drawing and I go, okay, this is really the integral from a to x, f of t dt equals the limit as n goes to infinity of k equals 1 to n. Right? So the reason I remember that is I've got n rectangles, in this case 3. And then I look at it. Well, it's f of xk times change in k. And now I need to write what these are. Well, each one of these, change in k, I'm sorry, we're changing x, not k. Now, I remember that change in x equals x minus a over n. And then I've got this f of xk bit, and I say xk, x0 equals a, and then xk equals xk minus 1 plus change in x. And that gives me all these little pieces. And you can use t or you can use x, either way. If you wanted to write it in terms of t, which is actually a better way to write it than the way I did it, it would look like this. This is a much cleaner way to write it. In fact, it's better, but I didn't do it in this. That would be a better way to write it. I didn't write it that way in the notes originally. But that would be a better way to write it with change in t. Are there any questions about that? So how do we feel about this 1 to 5, this definition? As I said, it's a tricky one. For me, it's easier if I remember the rectangles first. If I draw my picture, it's easier for me to remember the definition. All right, and remember to draw your pictures, because pictures are worth partial credit on tests if you mess it up. Okay. All right. And here we got some straight old plain antiderivative problems. Well, let's see here. I don't remember all these. So what I'm going to do is I'm going to make up my chart real fast. I'm going to do sine. Oops. Cosine, cosine, negative sine. So negative sine, sorry, not negative sine. Negative cosine is sine. This is g. This is f equals g prime. Let's see. What else do I have? I have, and then I'm going to make up, so I've got arc sine, and that's 1 over the square root of 1 minus x squared. And then I've got arc cosine, which is negative 1 over square root of 1 minus x squared. Arc tan, 1 over 1 plus x squared. Let's see. What else do I have here? I want e to the x is simply e to the x. That's boring. And ln of x is 1 over x. So I made my little cheat sheet because I'm doing antiderivatives. Okay. And then what I'm going to do is just take the antiderivative, because that's what this integral sign means with no bounds. If I don't have any bounds, this means just take the antiderivative, right? The indefinite integral. And we covered that last time. So I know that this is actually going to be, well, I look at my chart, and this is on my chart. You see how I made my chart, and then I found this right there. That's on my chart. So what I'm going to do is I'm just going to write, oh, that's arc sine of x plus c. And I found that because I made my chart. So 1 to 5, how do we feel about this? The important thing here is all I wanted was the antiderivative, and I made a chart. If you make the chart, I'm telling you, it makes your life so much better. You just pop them out real fast at the very beginning of the test, and then you refer to it again and again. It means take the antiderivative, not the derivative. Okay. So the question was, an integral symbol with no bounds means take the derivative? No, it means take the antiderivative. All right. Now let's look at this one. This one's a little trickier. This one I don't have, this one does not appear on my table. So now I'm about to get suspicious on this. Okay. This one doesn't appear on my table. I'm going to get suspicious. All right. What I'm going to do is I'm going to say, okay, if y equals the square root of 1 minus x squared, that means that y squared equals 1 minus x. Oh, it's a circle. And the square root of 1 would be the radius. That's just 1. Okay, so I know it's a circle. So what I'm going to do is I'm going to draw it out. This is a circle with radius 1, and I want the top half. So a circle with radius 1 goes from -1 to 1 with 0 here. Now, and I know I want the top half because I've got the positive square root. Now I'm going to look at this, and I'm going to shade the region that I want. The region I want goes from -1 to 0. Okay, well, that I can do. I know the area. It's a circle. So my AUC, this right here is a quarter of a circle. Okay. So I look at this and I go, okay, well, it's 1/4 pi times r, which is 1 squared. Well, 1 squared is easy, and that is pi over 4. How do we feel about that? 1 to 5. Because it's a little tricky. I'm using the idea that this is an area, and I don't use FTC2. I don't do trig substitution, which is the other way to do this. I don't do any of that, right? If you went online and you watched a bunch of Khan Academy videos, they're telling you to do trig substitution, all this jazz on it. You don't need to do that. It's not that. It's hard because it's simple, and because it's simple, it throws you, right. This is, you've got a pitcher throwing fastballs, and all of a sudden he throws a changeup right down the middle. You're not expecting it. That's what makes it hard. It's not a hard pitch to hit if you know it's coming, but if you don't know it's coming, it's a very hard pitch to hit. Okay, so the question is, why do we have to do the area of a rectangle plus the area of a cortical circle for some that have a larger radius? Well, it depends on what it is. Like if I had a +1, that'd be a rectangle on top of a circle. So some of these I'm going to use a combination of tricks, and there are a bunch of them on the bootleg that do this. Okay. All right. Yes, this would be the instant definite integral. I don't need anything. It's a circle. I know it's a circle. I know the formula for a circle. I take the circle. Okay. Now, this next one is another indefinite integral, and it's got three pieces. So the first thing I'm going to do is I'm going to break this up. They're all in sums, so I'm going to do 4x dx plus, and I don't have to do this. I mean, I could approach it without doing this, plus sine x dx minus e to the x dx. All right. Excuse me. Well, that first one, what is the integral of 4x? What's the antiderivative of 4x? Well, I'm going to have an x squared involved, and I'm missing a 2. Plus, okay, now I've got a sign here. I look at my chart, okay? I don't try to do this without my chart. I come back up and I look at my chart, and I go, okay, if sine is here, that means I've got negative cosine. So this becomes a negative cosine. Minus, and then I look back at my chart, I've got e to the x. E to the x is its own antiderivative. And then I've got this c that's just hanging out, the constant. Now, I took an antiderivative. What am I going to do? And I'm going to look. Does this agree with that? Yes. Always take the derivative to check. All right. Compute the antiderivative. 1 to 5, how do we feel about this problem? Four x squared. So the question is, what if you did 4x squared over 2? Well, that's the same thing as 2x squared. That's identical. They're the exact same thing. Okay. All right. This next one is 1 over x. Now, this can be a trap. If this had said negative 1 to e, what would my answer be? My answer would be does not exist because you're trying to do an antiderivative over somewhere where the thing's not defined. All right, that would have been bad. But here I've got 1 and I've got e. Oh, so the question is, would you lose marks if you don't check? I didn't tell you had to check. Okay, so if you look at the instructions, if you use the area state, I did not say you had to check. And here I didn't check because it was one piece. If this had been multiple pieces, I should have checked. But here, and arc cosine is 1 over 1 minus x squared. I just, I make sure I do that one and not that one. Sorry, arc sine. I make sure I don't want to do arc cosine. But on this one, it had multiple pieces, especially what's here with a parabol. I check it. And then these are nasty because you can wind up screwing up the signs because you go the wrong way. That's one reason why you want to keep taking derivatives, not antiderivatives. You want to make this chart by taking your derivative so that you have it to refer to. Okay. All right. So this one right here, I'm going to apply FTC2. And it's going to be G of E minus G of 1, G of X equals Ln of X, G prime of X equals 1 over X, X is greater than 0. Okay. Since X is greater than 0, I know the antiderivative, I know an antiderivative is the natural log of X. If this had crossed 0, or if this had been negative, I would have had log of negative X. If I had, if I was crossing 0, this would be does not exist. So I'm going to plug that in, my G, and I get Ln of E minus Ln of 1. And the Ln of E is 1, and the Ln of 1 is 0, and that equals 1. How do we feel about that one, 1 to 5? Okay, so we seem to be getting comfortable with these, at least a little bit. Okay. All right. Are there any questions? Go ahead and ask them while I switch over to the class, the stuff we're doing today. All right. The question is, why can't I use FTC2 for the circle question? You can, but you have to do trig substitution first, and it's very ugly. The antiderivative for that thing is not clean and beautiful, okay? It's not, you can take one, but you have to use trig substitution, and you're going to wind up with something that's very unpleasant. And that's a Calc 2 issue. But the point of this thing is to remember that area is the integral, and the integral is area. So the whole point of this is to remember that thing. Okay. Good questions, all. All right. So what we want to go over is the Fundamental Theorem of Calculus. And this is a beautiful proof. And I'm not trying to trump it up. No, it really is a beautiful proof. If you don't think this is a beautiful proof, I think there's something wrong with you, or maybe there's something in the wrong way I explained it that was wrong, because this is beautiful. So what is it we want to show? Our strategy is this. We're going to do the proof of FTC1 first. Okay. All right. So what is it I want to show? Okay. I want to show the following, right? What is it I want to show? Okay. So what I want to show is the following. I want to show that d over dx of a to x f of t dt equals f of x. where f is continuous. All right. So that's the big thing I'm trying to show here. 1 to 5, how do we feel about that? That's what I want to show. I want to show that if f is continuous, then this thing's derivative equals f of x. All right. We'll leave some space for the strategy. Let's dig in here. Now, I don't want you to get bogged down in the details. This is a big picture theorem, okay? And it's 2 big pictures, to be precise. Let's talk about this. Well, for simplicity, let's write a of x equals the integral from a to x, f of t, dt. Let's assume x is great. Let's assume, and let's show. So the question is, what is a prime then? All right. So let's do that. The definition of the derivative, a prime of x equals the limit as h goes to 0 of a of x plus h minus a of x all over what? All over h. Okay. Well, what is it I'm talking about here? Well, let's write this. What are we talking about here? We're talking about this as a picture. Let's see. Let's draw the picture. Let's draw the picture about what's going on here. I want those to be black. Where's the black? There it is. Then click there. Come on, give me something other than that. And now we want the picture. So here's f running around. All right, it's nice, it's continuous. Here's my base point. Here's x. And over here is x plus h. How do we feel about that picture, 1 to 5? All right. We just have a picture of f. But no, I'm drawing what I'm talking about here. I've got some f that's running around. I've got some base point a. I've got some point x, which is fixed. We'll even write that. I'm going to fix x. Okay, so a is something fixed. X is something fixed. Right? Because now I'm talking about a limit. When I do this derivative, I fix x. And I talk about the limit as h goes to 0. So what I'm talking about is I've got some width, which because they're French, we call it h. So I've got h for width. Now, I want to get a handle on this piece. I want to get a handle on a of x plus h minus a of x. Well, what am I looking at? A measures area. So what I want is the area in green minus this area here that I've just realized yellow is not going to work for that because it doesn't show up. That doesn't work either. Minus this area in pink. Okay? I'm sorry, minus the area. I'm sorry, that's wrong. I want the area in green minus this area here. Okay? I want the area of from a to x plus h. I want the area of a to x plus h minus the area of a to x. Well, what is that? That's just the area from x to x plus h. How do we feel about that, 1 to 5? So this is the whole thing I want. If you want the formula for it, okay, you can do it with a formula. Right, I've got the limit as h goes to 0. The formula way would be this. I've got a to x plus h f of t dt minus the area from a to x f of t dt, which equals the x to x plus h f of t dt from a formula from before. Right? That's one of those property formulas that we dealt with last time. All right? It's boring, but I can do it that way. So I don't want you to do it this way because I want you to, let's move boring over here. I don't want you to do it this way because it loses the picture idea. But I do have this formula, this idea that I went from, where was it? Yeah. Oh, I gotta minimize that. Go here. Go here. So I did have this last time, right? This piece comes from this formula here. So I can use that formula. But the intuition is much better if you do it the other way. Okay. All right. You know what? I hate you. You want the boring way with the formula, you can get it on the notes. So go away. Boring way goes away. Okay. I mean, you can watch it again, right? It's a video, so you can watch it again and go pause and then pull it back up, or you can see the notes. But that's boring. So what I want to show now is I need to show that the limit as h goes to 0, x to x plus h, f of t dt over h equals f of x. All right, so what we're talking about now is this area right here. Well, let's zoom in on this picture. It won't let me zoom in anymore. Let's zoom in on this piece. Matter of fact, let's draw a new piece. Let's talk about that piece right there. No, stop doing that. Forget it. Ha ha ha. I defy you. Okay. Let's talk about this piece. That's actually more piece than I wanted to talk about. There we go. We're going to zoom in here. And what we're going to go is we've got x to x plus h okay? And I've got something that looks like this. How do we feel about that 1 to 5? I've just zoomed in the picture a little bit. And what I want to do is I want to get at this area. There's this area here that I want to get at. Now, what I'm going to do is I'm going to estimate this using one rectangle, just one. So what I'm going to do is I'm going to draw the lower rectangle. Right, the area I want is this area that I'm going to put in lavender here, okay? This is the area I want. That's the actual area. Well, what I'm going to do, I can get under this. I can always have an underestimate. Remember our lower Riemann sum. Now, our lower Riemann sum nope, that was the day that everything went wrong. That's high, that's low, boring, boring, boring. But the point is there's this thing here called the lower sum. Okay? Now, I don't care about the whole bit. What I care about is this piece right here. Okay? So if I come back here, I could get at this by using one rectangle. I could estimate the lower area. Right? The width of this thing is still h. And my lower estimate would be as follows. This lower rectangle, what would be its size? Well, it's h for its width times the min of f x plus h. Now, remember this function right here, which we did right before the test, right? The min and max function. This min was this annoying function, but it looked like this, right? This is the function right here, right? It's the one that's always lower. So that will get me that rectangle. How do we feel about that 1 to 5? Just, I want that lower rectangle. Okay. Sorry. And that's the entire point of doing these lowers and uppers. Well, I can do the exact same thing that's an upper. And I get an upper estimate. Okay. How do we feel about that 1 to 5? These are just rectangles, right? This is a height. Both of these are heights. Right? This is a y value. This is the width. Okay. All right, and this is true for every h. Okay. What's coming? What's coming? All right. So if h is greater than 0, no one wants to say in chat what's coming. If h is greater than 0, I divide through by a positive number, and I get min is always less than or equal to this, which is less than the max. And if h is less than 0, flip the signs. It's boring details. Okay. Now, since f is continuous, both the max and min functions are well defined and continuous. That means that the limit as h goes to 0 of min fx x plus h equals the limit as h goes to 0 of min that should be there, min fx x plus 0. Oops, I'm sorry, I don't need that. All right, this thing is continuous, so I can direct substitute. Yeah. Well, what is min fx of x? If I'm here at my base point and I go no distance, what's my minimum? That minimum is simply f of x. Right? Because I didn't go anywhere. Likewise, How do we feel about that? 1 to 5. I've done it. I've shown what I wanted to show. And it's really 2 pictures. You want to write an introduction for this? Let's do it. Proof of FTC. What do I want to do? Strategy. Oops. I use a diagram to show that that's the derivative I want. That's how I would write the strategy for this. I just have to remember the diagrams. I don't have to remember all of these details. What do I need to remember? I need to remember this diagram and that diagram. Those are the 2 key pieces to this whole thing. This whole thing boils down to these 2 diagrams. If I understand what it is I'm doing, everything else is 2 diagrams. How do we feel about that? 1 to 5. The big picture. The big picture is the 2 diagrams. Now, as I said before, the boring details are in here. If you pull up that PDF document, you can see the absolutely boring details for this thing. Here I've listed all the stuff, but don't get lost in this. Keep an eye. Now here, what I did on this one is I only did one side, so I didn't have to deal with this little note that I made. And I also changed my notation a little bit, but it's really the exact same proof. And it really is. It really is don't get lost in the details. Remember the big idea. The big picture is I'm after this marginal area. Okay? And when you think about what that is, what the derivative actually is, it's saying what's going on at the margin. Well, here, my marginal area is what's important. Again, I'm after the marginal area. And then I get an estimate. I use an upper and a lower, and I just squeeze. I do 2 cups. Okay. All right. FTC2 is an afterthought. Okay. All right. Now, of course, everyone's got the question, is this going to be on the test? Okay, fine. I see the question in stamp. Yep, somebody asked it. I flipped back. Somebody asked, is this going to be on the test? And then it even got a thumbs up. Okay. How can you not know? It's beautiful. It's a thing of gorgeous beauty. If you really understand this proof, you're like, oh, it's beautiful. Now, um, most of the years, what we do is we say, prove the fundamental theorem of calculus. And then we let you choose, because there's another proof of this thing that proves FTC2 first and then FTC1. So normally, and some professors prefer that. I personally think that the proof of FTC2 without FTC1, the other way of doing this is just like, you take this absolutely beautiful thing and then you use the mean value theorem like a sledgehammer and go beat it into submission with the mean value theorem. And you just keep applying the mean value theorem. And I don't like it. It looks ugly. There's no intuition at all behind that proof. Okay. Proof of FTC2. It's a rabbit. And then I'll show you the rabbit. All right. So what do I want to show? I want to show if G is any antiderivative of F, then with continuity and blah, 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 blah. Here, I need to add something here to this. Wait, I want. There we go. That's my reaction to your question. If G is any antiderivative of F, then the integral from a to x of f of t dt equals g of x minus g of a. Strategy. What am I going to do here? You know what? I'm going to like do something silly here. All right, and it's got a rabbit. The rabbit is as follows. And there's the rabbit. How do we feel about this rabbit? I've got no width. That means that this right here is just that. So what I've got is it's a technical rabbit proof, and it just pops off. Okay, if G is an antiderivative of F, okay, and A is also an antiderivative of F, that means they differ by a constant. Okay. So there exists a constant C. I'm going to use U instead of X because I've got an X floating around. So because I've got an X floating around in the statement of my theorem, I'm going to use a U. I could have used a T as well. Either one would have worked. Now we'll do A on this side. I just want it to come out clean. A of U equals G of G of U plus C. And now it's just a long train of equality, right? I've got that the integral from A to X, f of t dt equals right? This, by definition, is A of X minus A of, oops, sorry, that's the wrong, yes. This right here is the definition of A of X. Now I subtract my rabbit. Okay. And now I just substitute in this equation for this. So I've got, because of this right here, I'm going to substitute this here twice. Right? That's why I used the U. Okay. And now it just falls out, right? G of X plus C minus G of A minus C equals, the C's cancel. Handy dandy. And all I'm left with is G of X minus G of A. It's boring. It's basically a corollary. And I know I did bad things and I forgot that. So that's all I did. It's just a rabbit proof. As a matter of fact, my strategy is longer than the whole bloody proof is, isn't it? Once you understand what you're after and you remember this little piece, this corollary for the mean value theorem, the rest of it just pops off. How do we feel about that? 1 to 5. It's just a rabbit proof. Okay. All right. Well, that's it. So we did what we wanted to do. The things we wanted to do today was we wanted to prove FTC1 and then we wanted to prove FTC2. I cannot emphasize this enough. Focus on the big picture. As a matter of fact, focus on the two pictures. If you have the two pictures and then you understand what you're doing, it all just flows. You don't have to memorize this proof like you would the proof for the product rule, okay? This is not one of those proofs. If you try that, you're going to get lost in the notation. You don't want to get lost in this proof. You want to focus on these two big pictures, okay? Now, for the question, is this going to be on the exam? Normally what we do is we have a question that says, prove FTC1 without using FTC2, or prove FTC2 without using FTC1. Or we have the proof for the diet versions of each, where we say, prove FTC1, you can use FTC2 if you feel so desire, or, one of the other ones, right? So sometimes we've given you choice, sometimes we give you choice about which part to prove, and sometimes we give you choice on whether or not to prove it using the other part. This year, we've decided to go with true-false questions from the proof. So there are true-false questions that have pieces like there are true-false questions that have pieces of this proof in it. You have to decide if what it's doing is intelligent or not. So instead of asking you to memorize the proof and jot it down straight, we're asking you to actually understand it. Are there any questions about that? Okay. There's a question about having a list of proofs, theorems like that for the exam. I will look at we're having a meeting this evening about what we're going to be telling students about what's on the exam. If at the end of that meeting I have enough information to actually generate one, I will. If I don't at the end of that meeting, I won't. So I need to get clarification from the other instructors what exactly we're supposed to tell you about the exam. Are there any other questions? Okay. Well, that's it for me. I am ending 1 minute late. I started 1 minute late, so that's convenient. And I will see you guys later.